In this session, we are going to discuss about ZPF and ASA methods of finding out voltage regulation of alternator. ZPF stands for zero power factor and ASA stands for American Standard Association. So first method is ZPF method. ZPF method is also known as Portier method. In Portier method, we are creating a triangle known as Portier triangle in order to separate the components of synchronous reactance. So synchronous reactance is the total reactance of the synchronous machine, which includes leakage reactance and armature reaction reactance. We know in alternator, armature current generate armature flux, and this entire armature flux is not linking with main flux. So those part of the flux which is not linking with main flux is known as leakage flux. As armature current is time varying one, leakage flux is also time varying one, which induces a self-induced EMF in armature. So the nature of this self-induced EMF is that it opposes the actual induced EMF. Therefore, net induced EMF is getting decreased. Thus, leakage reactance represent an EMF concept because due to the presence of phi L, an EMF is inducing. That induced EMF is N into d phi L by dt, which is equal to L into di by dt, which is equal to omega L into I. This is the induced EMF due to the presence of leakage flux, which opposes the induced EMF. This opposition creates net reduction in induced EMF. Therefore, leakage reactance represent an EMF concept. XA represents a fictitious reactance to consider armature reaction effect. We know in the case of motor or generator operations of a synchronous machine, armature reaction generate or creates a voltage phasor, say EA, and that phasor EA and IA resembles the characteristics of a pure inductive coil. So armature reaction effects can be considered by means of a fictitious reactance XA. Since the effect of armature reaction is either increase or decrease MMF or flux under different loaded condition depending on power factor of operation. In the case of lagging power factor, net flux is decreasing due to demagnetization. Under leading power factor, net flux is increasing. So the effect of armature reaction is either increase or decrease the MMF. So XA represents and MMF concept. Synchronous reactance of the machine contains two parts, XL. XL represent EMF concept, reduction in EMF, and XA represents reduction or increase in flux. That is, XA is MMF concept. In EMF method, XA is taken as additional leakage reactance. Therefore, excess synchronous reactance becomes an EMF concept. That's why this method is termed as EMF method. But in MMF method, XL is taken as additional armature reaction reactance. Therefore, excess become an MMF concept. But in ZPF method, we are combining good aspects of EMF and MMF method. In ZPF method, XL is treated as leakage reactance as it is, or leakage reactance is considered as EMF concept, and armature reaction effect is considered as MMF concept. This method separate armature leakage reactance and armature reaction reactance effectively. Therefore, this method gives more accurate results. Coming to the step to be followed in ZPF method, we need to conduct three tests on the given machine. One is open circuit characteristics, which gives the variation of no load induced EMF with respect to field current corresponding to rated speed. Second test is ZPF characteristics. Here we are plotting the variation of terminal voltage of the machine with respect to variation of field current while delivering rated armature current under zero power factor load condition. Then the third test is we need to measure effective armature resistance per phase. Based on the data available from these tests, we need to draw open circuit ZPF characteristics and air gap line. So first of all, for better understanding, let's draw the phasor diagram of alternator under lagging power factor condition to generate internal induced EMF E dash. Here V is the rated terminal voltage, I is current which is lagging by an angle phi, I into Ra which is in phase with I into XL which is leakage reactance drop which is leading I by 90 degree, and this I into XL we can directly obtain from 48 triangle. The sum of voltage, all these voltage gives E dash. Then we need to draw open circuit characteristics. Then we need to draw ZPF characteristics. Point F is the first point of ZPF characteristics where the voltage is zero. Therefore, the field current corresponding to rated armature current under short circuit condition. So after plotting ZPF characteristics, we need to draw air gap line which is the tangent to the initial portion of open circuit characteristics. Air gap line represents the OCC of the machine if there is no saturation. As we discussed, the point F gives the field current required to circulate rated armature current under short circuit condition. Why? Because terminal voltage is zero. This field current OF contains two parts. One is the field current to compensate armature reaction effect IFA, and second part is the field current to compensate the leakage reactance drop. Then second step is to draw 48 triangle. So corresponding to V rated terminal voltage, draw a horizontal line parallel to x-axis which will meet at ZPF characteristics point B. Then mark point C on this horizontal line so that BC is equal to OF. Then we need to draw a parallel line which is parallel to air gap line so as to meet this line at point D on open circuit characteristics. Then we need to join B and D so that it forms a triangle BCD. Then from point D we need to draw a perpendicular bisector to BC so that it will meet at E. In literature, we can see that either BCD or BED is termed as 48 triangle. Anyway, we are mainly interested in this portion DE, which gives I into XL drop. So from this 48 triangle, we can separate three components. One is I into XL, and second one is this portion BE, that is field current required to compensate armature reaction, and EC, that is field current to compensate leakage reactance drop. That is, first part is leakage reactance drop, DE gives I into XL, from that XL is equal to DE by I. We can find out leakage reactance. Second one is field current required to compensate armature reaction IFA, and third one is field current required to compensate leakage reactance drop. So after this, we need to calculate E dash, that is internal induced EMF E dash. That is the third steps, which is the phasor sum of voltage and up to leakage reactance drop. This gives E dash. Alternatively, we can derive the expression for E dash as V cos phi root of V cos phi plus I into Ra whole square plus V sin phi plus or minus I into XL all square, plus for lagging power factor and minus for leading power factor. Corresponding to E dash, we need to measure the field current. That is, what is the field current required to generate internal induced EMF under open circuit condition, that is known as IF1. For that, we need to measure E dash, proceed it into OCC, then measure the field current IF1. So IF1 gives the field current to generate E dash, internal induced EMF under open circuit condition. Then IF2, the field current required to compensate armature reaction, that is nothing but BE, which is obtained from 48 triangle. Once we got IF1 and IF2, we can find out the resultant field current IFR. This equation we are going to derive in different power factor condition. So once we got the resultant field currents by means of these equations, we need to measure no load induced EMF corresponding to this IFR from open circuit characteristics. So mark IFR, and we need to measure the E0 corresponding to this field current. Once we got E0, we can calculate voltage regulation by means of this expression V0 minus V by V into 100. So this is the procedure to be followed in all power factor of operation. Let's see the derivation of IFR and procedure in detail for different power factor of operation. Yes, first of all, let's discuss lagging power factor condition. We let V is taken as a reference phasor. I is lagging V by an angle phi, and we need to draw all the drops, that is I into RA and I into XL. This is I into RA, which is in phase with I, and I into XL, which is leading I by 90 degree. Then this gives E dash. Angle between, let's say the angle between E dash and V as alpha, F1 is leading E dash by an angle 90 degree. Then under short circuit condition, the power factor of operation is zero power factor lagging. So the armature reaction effect is fully demagnetization. The field current required to compensate armature reaction effect is considered by an anti-parallel phasor to I, that is IF2 is anti-parallel to I. Then we need to find out resultant field current IFR. So this is the resultant field current IFR. And now let's see the different angles. So angle between IF1 and I is 90 plus up to this 90 degree, and this angle is phi plus alpha, so 90 plus phi plus alpha. The angle between this IF1 and this IF2 is 90 minus phi plus alpha, so that this entire angle I and this IF2 become 180 degree. Then this angle between IF1 and this IF2 is 90 plus phi plus alpha. So as the angle between this phasor, which is preceded by IF1 and IF2, is 90 minus phi plus alpha. So please note this angle between IF1 and IF2 as 90 plus phi plus alpha. That is required for finding out the expression for IFR in coming slide. Then mark this point A, B, C, D like this. Let's create two right angle triangle from here. So let's proceed I phasor down. Then we can draw from point B. Let's draw a perpendicular bisector to this extended line so that it will meet at point E. From point C, similar process we can do so that it will meet at point F. Now let's consider two triangles AED, that is two right angle triangle AEB and AFD. So considering the first triangle AEB, the hypotenuse is voltage. Angle between AB and AE is phi. Therefore, AE gives V cos phi and BE gives V sin phi. So CF is also V sin phi. This is V cos phi, and EF is nothing but I into RA. This same projection BC projection is here, so I into RA. Now let's find out the expression for E dash. The angle between E dash and I is phi plus alpha. So E dash is nothing but root of AF square plus BFD square. AF is equal to V cos phi plus I into RI whole square plus this part V sin phi plus I into XL whole square. This I into XL is obtained from Portier triangle in ZPF method. How to obtain angle phi plus alpha? It is nothing but tan inverse opposite side by adjacent side. So opposite side is V sin phi tan inverse V sin phi plus I into XL divided by V cos phi plus I into RA. Then let's draw the steps in detail. First, we need to draw open circuit characteristics. Then we need to draw ZPF characteristics. Then air gap line. Then corresponding to V rated, note point B, mark point B on ZPF characteristics. Then mark C on this horizontal line so that BC is equal to IF. Draw a parallel to air gap line which will meet at D. Complete these Portier triangles, then draw perpendicular bisector DE to BC. DE represent I into XL. After getting I into XL, what we need to do is we need to calculate E dash. Corresponding to E dash, draw a line so as to find out the field current to generate internal induced EMF E dash under open circuit condition, that is IF1. Then we need to measure IF2 which is equal to BE. After finding out IF1 and IF2, IF1 is the field current required to generate E dash under open circuit condition. IF2 is the field current required to compensate armature reaction reactance. The angle between IF1 and IF2 is 90 plus 5 plus alpha. And this is the way to find out the resultant field current. So, since this angle is 90 degree, therefore this angle is 5 plus alpha, therefore this angle is also 5 plus alpha, and this phasor is IF2, therefore this projection that is IF2 sine 5 plus alpha, and this vertical component, this adjacent component for IF2 is IF2 cos 5 plus alpha. So IFR is equal to IF1 plus IF2 sin phi all square plus IF2 cos phi all square. So after simplifying, we can obtain the expression for IFR as IF1 square plus IF2 square plus 2 IF1 IF2 sin phi plus alpha. And sin phi plus alpha is a tan inverse V sin phi plus I into XL by V cos phi plus I into RA. So after finding out IFR, we need to proceed a line parallel to y-axis which will meet at tau CC and measure E0 corresponding to this IFR. Once E0 is obtained, we can find out voltage regulation. Similar to lacking power factor of case, V is taken as reference phasor, I is leading V by an angle phi, power factor angle. With voltage phasor, we need to add voltage drop so as to obtain the internal induced EMF. This is I into RA phasor which is in phase with I into XL which is leading I by 90 degree, and this is E dash in the internal induced EMF. And the field current to generate E dash under open circuit condition is IF1. So IF1 is leading E dash by 90 degree. And under short circuit condition, armature reaction effect is fully demagnetization. Therefore, it is drawn. IF2 is drawn anti-parallel to I. And we need to find out resultant field current likewise. The angle between E dash and V is alpha, and angle between E dash and I is phi minus alpha, and angle between I and IF1 is 90. This angle is 90 degree and this angle is phi minus alpha, therefore this angle is 90 minus phi minus alpha, therefore this angle is 90 plus phi minus alpha, and the angle between the projected IF1 and IF2 is 90 plus phi minus alpha, and please note this angle IF1 and IF2 under leading power factor is 90 minus phi minus alpha. Then we need to construct two right angle triangle just like in previous case to derive the expression for phi minus alpha. Proceed I phasor, then proceed IXL phasor. Likewise, then from the tip of V, draw a line like this, which is in parallel with this line. Now let's mark different points OA, B, C, D, E. Here the right angle triangle ODC. Here E dash. What is E dash? E dash is equal to OD square plus DC square. So we know in the case of first triangle ODA, V is the OA, which is nothing but terminal voltage is the hypotenuse. So OE is equal to V cos phi, and AE is equal to V sin phi. Therefore, BD, the total length BD is also is equal to V sin phi. Substituting these values in these equations, we can obtain E dash is equal to V cos phi plus I into RA whole square plus V sin phi minus I into XL whole square. So from this expression, we can calculate the expression phi minus alpha as tan inverse V sin phi, tan inverse V sin phi minus I into XL divided by V cos phi plus I into RA. These two things are required for deriving the expression for IFR. The angle between IF1 and IF2 is 90 minus phi minus alpha, and this angle phi minus alpha is tan inverse V sin phi minus I into XL by V cos phi plus I into RA. Coming to the steps, first we need to draw CC, then ZPF, then air gap line, then corresponding to rated we need to construct Portier triangles. From Portier triangles we can obtain XL. This is the phasor diagram. We need to, after obtaining IXL, we need to calculate E dash by means of this expression, and corresponding to E dash from open circuit characteristics, we need to find out IF1, that is field current to generate internally induced EMF under open circuit condition. Then IF2 already we found out from Portier triangle, which is the field current to compensate armature reaction effect. Once we got IF1 and IF2, draw this phasor diagram. The angle between IF1 and IF2 is 90 minus phi minus alpha. This is the resultant phasor. Let's create two lines like this so as to derive the expression for IFR. Let's consider points likewise A, C and D, and since this angle is 90 minus phi, so this angle is phi minus alpha, therefore this angle is also, so AC is equal to IF2 sin phi minus alpha, and AD is equal to IF2 cos phi minus alpha. So OB is equal to OC square plus BC square, and OC is nothing but OA minus AC. After substituting all these things in these equations, we can obtain the expression as IF1 square plus IF2 square minus 2 IF1 IF2 sin phi minus alpha. Once we got the resultant field currents, please mark this point in x-axis. Then find out open circuit voltage corresponding to this IFR, that gives E0. Once we got E0, we can find out voltage regulation. Coming to unity power factor condition, V is taken as a reference, I is in phase with V. We need to draw I into RA drops, which is in phase with I, and I into XL, which is obtained from Portier triangle and leading I by 90 degree, and this is our E dash. And IF1 is leading E dash by 90 degree, and IF2 is anti-parallel with I, and this is the resultant field current IFR, local things. Then the angle between E dash and V is alpha, angle between V and IF1 is 90 plus phi. Then angle between this angle is 90 minus alpha, therefore this angle is angle between IF1 and IF2, this angle is 90 plus phi. So this is very important, 90 plus phi. And let's mark different point like this, OABC. Consider triangle OBC. A dash is equal to root of OA plus AB all square plus BC all square. Substituting these values, E dash is equal to V plus I into RA all square plus I into XL all square. Then alpha is equal to tan inverse IXL by V plus I into RA. So coming to the steps, First we need to draw open circuit characteristics, then ZPF characteristics, then we need to draw air gap line, then we need to construct Portier triangle to separate I into XL drops. So this is I into XL. After obtaining I into XL, we need to calculate E dash by means of this expression. After calculating E dash, we need to find out the field current to generate E dash under open circuit condition, that is IF1, and IF2 is the field current which is obtained from field current to compensate armature reaction, which is obtained from Portier triangle as BE, that is IF2. Once we got IF1 and IF2, draw these phases. IF1 and IF2, the angle between IF1 and IF2 is 90 plus 5. Then this is the resultant field current. Draw two lines like this in order to derive the expression for IFR. The angle between this angle is alpha. Therefore, this angle is alpha. Therefore, this part is IF1 and this part is IF2 sin phi, and this part is IF2 cos phi. Therefore, IFR is equal to IF1 plus IF2 sin phi whole square. Root of IFR is equal to root of IF1 plus IF2 sin phi whole square plus IF2 cos phi whole square. After simplifying, IFR is equal to root of IF1 square plus IF2 square plus 2IF1 IF2 sin phi. Once we got IFR, we need to obtain E0 corresponding to this resultant field current, and we can calculate voltage regulation. Let's see one example of finding out voltage regulation using ZPF method. The following data pertains to a 5000 kVA 6600 volt 3-phase 50 Hz star connected alternator. Here they given open circuit parameters and ZPF parameters corresponding to field currents. Here we need to determine voltage regulation by means of ZPF method at full load and unity power factor. We are mentioning that armature resistance is 0, and we need to draw the phasor diagram. Given parameters are a line value of voltage is 6600 volt, therefore the phase value of voltage is 3810.5. Power rating is 5000 kVA. From this 5000 kVA power rating, we can calculate, and line value of the voltage, we can calculate the rated current as 437.39 ampere, and we need to convert line value of voltages into phase values. So this is the phase value of voltage corresponding to OCC, and this is the phase value of voltage corresponding to ZPF with respect to this field current. Here the first point of ZPF characteristics, the voltage is 0, that is under short circuit condition. The field current required to circulate rated armature current under short circuit condition is 32 ampere. So in OCC characteristics, the first point of ZPF characteristic is 32 ampere, that is OF. Then ZPF characteristics, air gap line we need to draw. Rated voltage is 3810.5 phase values. Then we need to draw the Portier triangle. BC we need to mark 32 ampere. Then from point C draw a parallel line parallel to air gap line and complete a Portier triangle. Then draw perpendicular bisector D to BC. That gives I into XL. So I into XL is obtained as 534.12. Once we got I into XL, we can calculate internal induced EMF E dash by means of this expression, and it is obtained as 3847.75. And we need to, next step is we need to find out IF1, that is field current to generate E dash internal induced EMF under open circuit condition. We need to extend one line from E dash corresponding to this value and not IF1, and IF1 is obtained as 76.375 ampere. And IF2 is nothing but field current to compensate armature reaction effect, that is nothing but BE, and BE is obtained as 22.25 ampere. So once we got IF1 and IF2, we can calculate resultant field current. Okay, resultant field current. How to calculate alpha, it is explaining in next slide. So once we got IFR is obtained as 82.46 ampere by means of this expression. We need to, once we got IFR, we need to extend a line from IFR so that it will meet at OCC. Corresponding value of phase value of no load induced voltage gives no load induced EMF E0. Here E0 is obtained as 4000 volt. So this is the actual graph which I plot in origin. Alpha is obtained from this expression and is obtained as 7.98 degree. Substituting all these parameters, IFR is obtained as 82.46, corresponding to 82.46. Proceed a line parallel to y-axis which will meet at OCC, and corresponding voltage is obtained as 4000. So voltage regulation is obtained by means of this expression by substituting E0 and V likewise. So the voltage regulation obtained by ZPF method under unity power factor full load condition is obtained as 4.97%. Coming to the phasor diagram, V is taken as the phasor reference phasor. I is in phase, that is 437.39 ampere. Then IXL, which is obtained from Pottier triangle, which is 534.12, which is leading I by 90 degree. Since RA is not there, because RA is 0. And this is A dash. A dash is obtained as 3847.75 volt. Then IF1 is leading E dash by 90 degree. IF1 is obtained as 76.375 ampere, and IF2 is anti-parallel with I, 22.25 ampere, and we calculated IFR as 82.46 ampere, and alpha, this angle between IFR and IF1 and IF2 is 90 plus I alpha. Alpha is obtained as 7.98 degree. So once we got all these things with respect to IFR, we can draw the E0 phasor. Okay, this is E0 phasor around 20 degree with respect to IFR, and this phasor, this E0 and E dash phasor is nothing but I into Xi, and total drop A to this is I into Xs. So this is the phasor diagram of this problem. Coming to next method of finding out voltage regulation, that is ASA method. ASA stands for American Standard Association. So far we discussed about EMF, MMF and ZPF method. EMF method gives more voltage regulation than that of actual. Therefore it is termed as pessimistic method. MMF method gives less voltage regulation than that of actual. Therefore this method is termed as optimistic method. Among these three methods, ZPF method gives better result for turbo alternator, that is non-salient pole alternator, as it effectively separates MMF and EMF components, that is leakage reactance and armature reaction MMF, in effective manner. In all these three methods, we are not considered saturation effect of the magnetic circuit. In ASA method, saturation effect of the magnetic circuit is considered effectively, and it is the combination of good aspects of MMF and ZPF method. This method gives better result in all type of alternator. And it is to be noted that voltage regulation obtained by EMF method is greater than that of ASA method, and that of ASA method is greater than that of ZPF method, and voltage regulation obtained by ZPF is greater than MMF method. Very low value is obtained in MMF and greater value is obtained in EMF method. ZPF is preferable for turbo alternator. In salient pole machine, ZPF method gives more error. In that case, we can use ASA method for finding out voltage regulation. Coming to the step to be followed in ASA method. Just like in ZPF method, we need to conduct ZPF characteristics, OCC characteristic, and we need to measure armature resistance per phase. The first step is plot OCC, ZPF and air gap line. After that, we need to construct Portier triangle to obtain IXL drop, that is leakage reactance drop. Then the third step is to obtain field current corresponding to V rated from OCC without considering saturation, that is up to air gap line. This field current is IF1, that is corresponding to V rated, proceed a line parallel to x-axis which will meet at air gap line, then proceed downward, that gives IF1. Then fourth step is obtain field current IF2, which is exactly same as that of MMF method, that is field current to circulate rated armature current under short circuit condition. Here it is equal to OF. Then find out the resultant of IF1 and IF2 based on the method we followed in MMF method. That is IFR dash is equal to square root of IF1 square plus IF2 square plus or minus 2 IF1 IF2 sin phi plus for lagging power factor and minus for leading power factor. After that, we need to calculate internal induced EMF E dash by means of this expression root of V cos phi plus I Ra all square plus V sin phi plus or minus IXL all square plus for lagging and minus for leading power factor. The seventh step is measure the field current distance IF dash between air gap line and OCC corresponding to E dash. Then obtain the resultant field current IFR, which is equal to IFR dash plus IF dash. Here IF dash consider the saturation effect of the magnetic circuit. Then corresponding to this IFR, from OCC we need to find out E0. Once we got E0, we can calculate voltage regulation by means of this equation. Coming to the lagging power factor of operation, first of all we need to plot OCC, then first point of ZPF characteristic, that is OF, which is equal to IF2. Then we need to plot ZPF characteristics. Then we need to draw air gap line. Then we need to construct Portier triangle corresponding to rated voltage, just like in ZPF method, and so that we can obtain DE. DE gives IXL. Then corresponding to rated voltage, proceed a line parallel to x-axis which will meet at air gap line at point G, then proceed downward. That field current is known as IF1. Now we can have IF1 and IF2. IF2 is OF, the first point of ZPF characteristics. Once we got IF1 and IF2, we can find out the resultant field current IFR dash, just like in MMF method. The angle between IF1 and IF2 is 90 plus phi. This is the resultant field current IFR dash, and we can draw two vertical lines and some lines like this in order to derive the expression for IFR dash. So IFR dash is equal to IF1 plus root of IF1 plus IF2 sin phi all square plus IF2 cos phi all square. So by simplification, we can have this expression root of IFR dash is equal to root of IF1 square plus IF2 square plus 2 IF1 IF2 sin phi. Then we need to calculate internal induced EMF E dash by means of this expression and proceed a line parallel to x-axis which will meet at air gap line and OCC, and measure the gap between air gap line and OCC, that is KL. This gives IF dash. Then IF dash is added with IFR dash in order to obtain resultant field current, that is IFR is equal to IFR dash plus IF dash. Then corresponding to this resultant field current, extend to upward so that it will meet at OCC and measure these no load induced EMF E0. Then we can calculate voltage regulation. Coming to leading power factor of operation, first of all we need to draw open circuit characteristic, then ZPF characteristics, then air gap line. Then corresponding to rated voltage we need to construct Portier triangle in order to obtain IXL drop. And after that, corresponding to rated voltage, we need to measure the gap between y-axis and air gap line, that is EFG, that gives IF1. and BC is equal to OF, that is field current required to circulate rated armature current under short circuit condition, is taken as IF2. Then we need to draw the phases IF1 and IF2. The angle between IF1 and IF2 is 90 minus phi. This is the resultant field current IFR dash. IFR dash is equal to root of IF1 minus IF2 sin phi all square plus IF2 cos phi all square. Simplifying, IFR dash can be obtained as root of IF1 square plus IF2 square minus 2IF1 IF2 sin phi. After calculating this resultant field current IFR dash, we need to calculate E dash by considering IXL, which is obtained from Portier triangles by means of this equation. After obtaining E dash, we need to measure the saturation effect, that is the gap between air gap line and OCC corresponding to E dash. That gives IF dash. Then the final resultant field current is the sum of IFR dash and IF dash. Mark this resultant field current on x-axis and proceed upward to meet on SCC. That gives E0. Once we got E0, we can calculate voltage regulation. Coming to unity power factor condition, first of all, we need to draw open circuit characteristics, then ZPF characteristics, then air gap line, then corresponding to rated voltage, we need to construct Portier triangle in order to separate IXL drop. After that, corresponding to rated voltage, we need to measure the gap between y-axis and air gap line. That gives IF1, and IF2 is same as that of Yamaha method, that is OF, the field current required to circulate rated armature current under short circuit condition. After obtaining IF1 and IF2, we can draw the phases IF1 and IF2 in order to find out the resultant field current. The angle between IF1 and IF2 is 90 degree. This is the resultant field current and it is obtained as root of IF1 square plus IF2 square. After obtaining IFR dash, we need to calculate internal induced EMF E dash by means of this equation and proceed parallel to x-axis. The gap between air gap line and actual OCC is KL. That gives the saturation effect. Consideration IF dash. Once we got IF dash, we can calculate the resultant field current. The resultant field current IFR is the sum of IFR dash and IF dash, and corresponding to this resultant field current, we need to measure open circuit voltage. That gives E0. Once we got E0, we can calculate voltage regulation. Let's calculate the voltage regulation of a 10 kVA 440 volt 50 Hz 3-phase star connected alternator. The machine is having the open circuit test data as below. Here the no load induced EMF is given in line values. With full load zero power factor, the excitation required is 14 ampere to produce 500 volt terminal voltage. This is one point in ZPF characteristics. Under ZPF characteristics, corresponding to 14 ampere, the terminal voltage is 500 volt. On short circuit, 4 ampere excitation is required to produce full load current. This gives the field current to circulate rated armature current under short circuit condition. This is first point in ZPF characteristics. We need to determine the full load voltage regulation at 0.8 power factor lagging using Yamaha method, ZPF method and ASM method. And we need to compare the result. Here we are assuming RA is equal to 0.22 ohm per phase. Coming to the solution, here the line voltage is 440 volt, that we need to convert into phase value. Phase value is 254.03 volt. Rated current can be calculated from power rating, and line value is equal to, rated current is equal to 10 into 10 raised to 3 divided by root 3 into 440 volt, and it is coming as 13.1216 ampere. This is the OCC characteristics after converting line values into phase values. Let's solve this problem firstly using MMF method. After suitably selecting the scale, first step is to draw open circuit and short circuit characteristics. Here, x-axis field current is taken as 1 division is equal to 1 ampere. And for open circuit characteristics, y-axis 1 division is taken as 15 volt. For short circuit characteristics, 1 division is equal to 5 ampere. And after selecting this scale, this is the OCC and SCC characteristics. Then we need to calculate E dash, which is equal to V plus I into RA cos phi. V is 254.03, I is 13.1216, Ra is 0.22 ohm and cos phi is power factor is 0.8. Then substituting this, A dash is equal to 256.34. Mark this 256.34 on y-axis. Draw a parallel line parallel to x-axis which will meet at OCC and proceed downward. That gives the field current to generate E dash under open circuit condition. That is, IF1 is obtained as 5.1 ampere. Then IF2 is the field current required to circulate rated armature current under short circuit condition, and IF2 is given as 4 ampere. Once we got IF1 and IF2, we need to calculate resultant field current by means of this expression. As cos phi is 0.8, sin phi is 0.6. Substituting IF1, IF2 and sin phi in this expression, we can obtain IFR as 8.15 ampere. Then corresponding to IFR, draw a line parallel to y-axis that will meet at OCC, then proceed, that gives E0. E0 is obtained as 320 volt. Then we can obtain voltage regulation by means of this expression, and voltage regulation is equal to 320 minus 254.03 by 254.03 into 100, and it is obtained as 26%. Let's solve the same problem using ZPF method. The first step is to plot open circuit characteristic and ZPF characteristics and to draw the air gap line. Here in ZPF characteristics only 2 points are given. This is the first point, that is the field current to circulate rated armature current under short circuit condition, that is 4 ampere. And second point is corresponding to 14 ampere field current, the terminal voltage is 500 volt line to line, that is 288.7 volt phase values. Corresponding to this voltage, we need to construct 40 triangle. From point B, mark point C such that BC is equal to this value, that is 4 ampere. BC is equal to 4 ampere. From point C, draw a line parallel to air gap line that will meet at point D in OCC. Then join BCD that form a triangle. That triangle is 40 triangle. From D, draw a perpendicular bisector to B and note this length DE. DE into voltage scale gives IXL drop. From graph, IXL is equal to 58.07 volt and IF2 is BE, it is obtained as 3 ampere. Then we need to calculate internal induced EMF E dash using this expression. Here we need to use IXL, which is obtained from 40 triangle. Substituting all these values, E dash is obtained as 294.6 volt. Then mark this voltage 294.6 volt on y-axis, proceed a line parallel to x-axis which will meet at OCC, that corresponding to this voltage, not this field current, that gives IF1. IF2 is already obtained from 40 triangle. Then in order to use this expression, we need to calculate phi plus alpha, and phi plus alpha is obtained by means of this expression, tan inverse V sin phi plus IXL by V cos phi plus I into Ra. Substituting all these values, phi plus alpha is obtained as 45.6 degree. Substituting 45.6 degree as phi plus alpha, IF1 as 6.643 ampere and IF2 as 3 ampere, we can obtain resultant field current as 9.034 ampere. Then corresponding to IFR, we need to proceed a line parallel to y-axis which will meet at OCC, that gives no load induced EMF E0. Here E0 is obtained as 330.28 volt. Then we can calculate the voltage regulation using this expression. Voltage regulation is obtained as 30.016%. Here it can be seen that voltage regulation using MMM method is 26%, Voltage regulation using ZPF method is 30%. Voltage regulation obtained by ZPF method is greater than that of EMF method. The third method to solve this problem is ASA method. Here we need to plot open circuit characteristics, ZPF characteristics and air gap line. And similar to ZPF method, we need to construct Portier triangle to obtain IXL drop. From graph, IXL drop is obtained as 58.07 volt and IF2 is same as that of EMF method, that is equal to 4 ampere. This is the field current to circulate rated armature current under short circuit condition. Then corresponding to rated voltage, proceed a line parallel to x-axis up to air gap line, then proceed downwards from this meeting point. That current gives IF1. Once we got IF1 and IF2, we can calculate IFR dash using this expression. Since cos phi is equal to 0.8, sin phi is equal to 0.6. Substituting these values, IFR dash is obtained as 7.52 ampere. In order to consider saturation effect of the magnetic circuit, we need to calculate internal induced EMF using this expression, substituting the value of IXL, which is obtained from Portier triangle, and this value of E dash is obtained as 294.6 volt. Corresponding to 294.6 volt, that is E dash, proceed a line parallel to x-axis which will meet at air gap line and OCC and measure the gap between this meeting point. That gives I saturated or IF dash. Then IFR, resultant field current, is the sum of IFR dash and IF saturated, and IF saturated is obtained as 1.16 ampere. Then the resultant field current is obtained as 8.68 ampere. Then corresponding to IFR, proceed a line parallel to y-axis that meet at OCC and no load induced EMF is obtained as 326.2 volt. Then we can calculate the voltage regulation using this expression, and the voltage regulation is obtained as 28.41%.